Okay. Hello everyone. Today we'll be looking at the third talk in the series of philosophy in physics, where we'll be looking at some examples in in the branches of physics itself. Earlier we looked at philosophy as a concept. Then we looked at philosophy in physics. Now we're looking at, how some of the concepts of philosophy in physics are applied in, concepts such as Newton's laws, Kepler's laws, or Maxwell's equations, and so on. Actually, there's a lot of things where a lot of these concepts where the philosophy of physics is applied. But if we were to do a talk on it, it would take way too long. So we've just narrowed ourselves to like 4 or 5 topics today. So it'll be so Ashwin will start right now. He'll be talking about Newton and Kepler's laws. So without further ado, I'll hand it over to Ashwin. Ashwin.
Next slide. Hey friends, my talk will be like a story, like little story. Like always, I'm starting with a little bit of history, and then I'll talk about Kepler's law, and then how Newton deduced gravitation from Kepler's law. So next. Next is nowadays, most of us, even a little mind knows that Earth is spherical. But earlier, at least most thought the Earth was flat. The first notable person to question that was Pythagoras. He also gave us a beautiful explanation that if Earth was flat, then why the hell does the ship disappear hull first? For nearly 1,000 years, Aristotle's view of stationary Earth at the center of a revolving universe dominated natural philosophy. A geocentric worldview became ingrained in Christian theology, making it a doctrine of religion as much as natural philosophy. The irony here is, it was a priest who brought back that Earth moves around the sun. In 1515, Polish priest named Copernicus proposed that the Earth was a planet like Venus or Saturn, and that all planets circle the sun. Afraid of criticism and punishment from the church, Copernicus did not publish his theory until shortly before his death. He was so afraid that he didn't want to publish his finding because on the day church had major control over society, and those who have stepped out from their Christian views were punished heavily. So we will see about in the next slide. The theory gathered few followers, and for a time, some of these who did give credence to this idea faced charges of it. Some were even murdered. Yeah, to put the word, they are murdered for science. Italian scientist Giordano Bruno was burned at the stake for teaching Copernicus' heliocentric view of the universe. But the evidence for a heliocentric solar system gradually mounted. Next. When Galileo pointed his telescope into the sky, hinted, he saw for the first time in human history that moons orbited Jupiter. If Aristotle were right, if Aristotle were right about all things orbiting the Earth, then these moons could not exist, right? Because these moons were revolving around the Jupiter. And Galileo also observed the phases of Venus, which also proved that the planets orbits the sun. While Galileo did not share Bruno's fate, he was tried and under Roman Inquisition was placed under house arrest for his life. Next slide. At about the same time, German mathematician Kepler was publishing a series of laws that describes the orbits of the planets around the sun, which are still in use today. These mathematical equations provided the accurate prediction of planets' movement under Copernican theory. In 1687, Isaac Newton put the final nail in the coffin for the Aristotelian geocentric view of the universe. Newton was very lucky because earlier to Newton, the church had major control over the society. While during Newton's view, the world was coming out of Aristotelian philosophy. They were exploring new things and they were more open to the scientific ideas. So Newton uh, had more freedom to express his views. Building on Kepler's law, Newton explained why the planets moved as they did around the sun, and he gave the force that kept them in check, its gravity. Think Kepler found that planets revolve around the sun, right? It is the effect. The cause of this effect is gravity. While Kepler explained the effect, Newton gave us the cause. So that it's like causality. Uh, for that only I have included this Kepler, Newton's derivation of gravity from Kepler's. Next slide. Kepler's laws of planetary motion. At around the age of 27, I think around the age of 27, Kepler became the assistant of a wealthy astronomer. His name was Tycho Brahe. He was very rich and he's also old. And Brahe asked the help of Kepler to define the orbit of Mars. Brahe had collected a lifetime of astronomical observations. He was collecting from the young age itself, which when Brahe did his observation, his work passed on to Kepler's hand. And Brahe was a geocentered person, and he withheld bulk of observation from Kepler, in part because he did not want Kepler to use them to prove Copernican theory, which he did. While Copernicus' theory rightly observed that the planets revolve around the sun, it was Kepler who defined their orbits. Using these observations, Kepler found that the orbit of planets follow three laws. Like many philosophers of his era, Kepler had a mystical belief that the circle was the universe's perfect shape, and that as a manifestation of divine order, the planet's orbits must be circular. For many years, he struggled to make Brahe's observation of the motion of Mars match up with the circular orbit, but Kepler can't. Next slide. uh, uh, Eventually, however, Kepler noticed that an imaginary line drawn from planet to the sun swept out an equal area of space in equal times, regardless of where the planet was in its orbit. Imagine he he drew a triangle out from sun to a planet's position at one point in time and its position at a fixed time later. So, say like 5 hours or 2 days or something like that. The area of triangle was always the same anywhere in the orbit. For all these triangles to have the same area, the planet must move quickly when it's near the sun. but more slowly when it's farthest from the sun. This discovery, which became the Kepler's second law of orbital motion, led to the realization of what became Kepler's first law, that the planets move in an ellipse, with the sun at one focus point offset from the center. Kepler first the what he in first he did the second law, and then from that second law he made into the first law. I don't know why this order is like that. I think second law should be first and first law should be second. And Kepler's third law shows that there is a precise mathematical relationship between a planet's distance from the sun and the amount of time it takes revolve around the sun, which is t squared is proportional to r cube. Next one. Thinking on Kepler's law, Newton uh, realized that all the motion, whether it was the orbit of the moon around the earth or an apple falling from a tree, followed the same basic principles. The Kepler's law inspired Newton, who came up with three laws of his own to explain the planets move as they do. If Kepler laws defined the motion of the planets, Newton's law defined the motion itself. He wrote, to the same natural effects, we must, as far as possible, assign the same causes. The cause was gravity. Previous Aristotelian thinking, uh, Stephen King has written, assigned different causes to different types of motion. But Newton unified all this. By unifying all motion, Newton shifted the scientific perspective to a search of large unifying patterns in nature. Newton's law of motion and gravity explained Earth's annual journey around the sun. Earth would have moved straight forward through the universe, but the sun exerts a constant pull, constant gravity on our planet. This force bends Earth's path towards the sun, pulling the planet into a almost circular orbit. So next, deduction of Newton's law of gravitation from Kepler's law. Uh, I don't know. It's like causality. Kepler knows the effect, but Newton derived the cause. So while most mechanics books follow the derivation of Kepler's law from Newton's law, let's see here how Newton's law can be derived from Kepler's law. And maybe after this talk, after 1 or 2 days, I will post notes for another type of derivation. It is also good. So let's look at this simple derivation. Let omega be the angular velocity and t be the time period, and m small m be the mass and capital M be the mass of the sun. We know omega is equal to 2 pi by t, right? And also the centripetal force on the planet is also force is equal to mr omega square. Substituting the value of omega here, we will get this 4 pi square mr by t square. Next. But Kepler already explained in his third law that square of time period is proportional to r cube. And putting the constant of proportionality k, t squared is equal to k r cube. Excuse me, guys. Yes. Meenakshi, can you go to the previous slide?
Yeah. You completely you went silent there for a minute. That's why I said.
I was not.
Yeah,
Uh,
yeah.
while substituting this time period in this second equation in the t square in the denominator, we get this. Here, the term 4 pi square by k is the um, constant, whereas the mr square, this is force is gravitational force is proportional to the mass of the planet and also the radius. We are getting this equation. So let's now, the only term remaining is the gravitation constant g and the mass of the sun. So from 4 pi square by k, we can find out that. So next. According to Newton, the gravitational attraction between the sun and the planet is mutual. The sun pulls the planet, and the planet, while not as strong as sun, it also exerts some force on the sun. If the force is directly proportional to the mass of the planet, it should also be proportional to the mass of the sun because the gravitational force is mutual. So we can say that 4 pi squared by k is proportional to mass of the sun, and which is equal to the gravitational constant multiplied by mass of the sun. Substituting this in the equation 4, we get the Newton's law of gravitation. The one thing I want to tell here is, I think I read Feynman's quote or Stephen Hawking's quote. I don't know, I forgot. Philosophy came around for. In my first talk, I told us philosophy as a set of questions and answers. Philosophy answers the major questions like how the universe is created, and is there a god, and how are we created, are we alone in the universe. These are the major questions that philosophy should answer. But nowadays thinking, like, most of the questions are now in the hands of the science students. So we can say that philosophy is handed over to physics. So nowadays, physics is the philosophy itself. So without further ado, I will hand over this session to Meenakshi, and thanks for listening.
Yeah, thank you, Ashwin. So next we'll be looking at other two concepts, mainly Maxwell's equations and relativity. Now, you might ask me why did I pick these two? The reason being that these two seem to stick to the concept of contiguity. Basically, the law of contiguity and antecedents, which we looked in the previous talk, which are related to causality, where you know two objects in the definition of contiguity, two objects should be in contact with intermediate objects in between. So we will look at Maxwell's equations. So this is the mathematical part of Maxwell's work, which is consistent in condensing the experimental laws, and we have a set of differential equations with the usual notation are, you know, divergence of d, which is equal to 4 pi rho, and curl h, which is equal to 4 pi by c into u, where u is the current density, and divergence of b is equal to 0, and curl of e plus 1 by c into b is equal to 0. So you might be familiar with some of these equations. They just look a tad bit different, but if you actually, substitute the symbols and try to jog your memory a little from what you've learned before, you would remember these. And these might be a little complex, and I will explain them in a way where we'll understand that contiguity is there, and rather not look into how the whole equation was derived as such. So we have d is equal to epsilon e and b is equal to mu h. So these are like these are like the two constants where d is the displacement field and b is the magnetic field. So this is d is relevant to electrical field and b is relevant to magnetism. So we'll give a simple example here. using Coulomb's law of electrostatic field, where we'll put B is equal to 0, H is equal to 0, and U is equal to 0. Then we'll be left with divergence of D is equal to 4 pi rho, and curl E is equal to 0. So B and H becoming 0 because these are relevant to magnetism, and Coulomb's law will rather be focusing on the electrical aspects. So yeah, the second equation with the one over here, right here, implies that we will get E is equal to the partial derivative of flux, basically. That there's a potential flux right here, and then this is what we get as the value of E, the negative of the partial derivative of flux. So in vacuum, we can where D is equal to E, we can obtain Poisson's equation using minus the divergence of E is equal to delta phi is equal to minus 4 pi rho. This seems a little obvious from what we have seen above here. And then as we go further, we can find a solution for this. Obviously, by using some obvious methods, we can arrive at the integral of rho by r into dv, which is equal to the value of flux. Provided the singularities are excluded, this formula expresses Coulomb's law for continuous distribution of density. So the continuous distribution over the volume. So basically the density is a continuous distribution over density. So that's why we have an integral right here, and that gives the flux over it. So in a similar way, one obtains for stationary states B is equal to 0 the law of Bio and Savart for the magnetic field of a current density U, current of density U. So we can try out some other methods, and from there we will also be able to obtain Bio-Savart's law, which is kind of the equivalent in terms of magnetism to the previous equations. So Maxwell's physical idea consisted in discovering the asymmetry in the equation 2, where the missing term 1 by c into d is in the second equation. So this one right here, equation 2, sorry, went a little ahead. This one right here. This is the second equation where we have 1 by c missing, 1 by c into d missing. And the logical necessity of this term follows in the fact that the existence of open currents, example, discharges of condensers through wires. So so Maxwell noticed this, and to solve the asymmetry, he decided to work on it a little. And in this case, the charge on the condenser changes in time. Hence, rho dot is not equal to 0. On the other hand, the equation 2, I should have labeled it as equation 9. But anyway, it implies that the divergence of U is equal to C by 4 rho, 4 pi, and the divergence of the curl of H, which is equal to 0. As we simplify it further and we equate that rho dot is not equal to 0, we can arrive at this. And the contiguity but because of this, we can see that the contiguity of rho dot plus divergence of U is equal to 0 is violated. How you might ask me how, but we'll look at this up here. So basically, we have rho plus divergence of U, and where we would have to put that in these equations, and that would mean that it would ultimately be contradictory, and it's not exactly connected. It's not exactly establishing a connection between the equations. So therefore, contiguity is violated. So we'll look at this. We'll get a better understanding of contiguity as we progress further. So to amend this, Maxwell postulated a new type of current bridging the gap between the conductors in the condenser with a certain density W, so that curl of H is equal to 4 pi by C into U plus W. So we'll get divergence of W is equal to minus divergence of U is equal to rho dot is equal to 1 by 4 pi divergence of D dot. So the simplest way of satisfying this equation, we can just put take all the divergences and simplify it and put it in such a way that we get W is equal to 1 by 4 pi D dot. So we can substitute this in Maxwell's equation, and therefore we can finally get the value. We can finally get 1 by C into D in the equation. So curl of H minus 1 by C D is equal to 4 pi by C U, which is right up here. So we will move further, and then we will take a look at how we put the divergence operation, and we can sorry, I already explained that. So yeah, so the complete symmetry between the electric and magnetic quantities is obtained, apart from the fact that the latter have no true charge and current. So and there's some symmetry that is maintained between the electric and the magnetic equations, which is up here. So we can, relate both of these. So the concept of electromagnetism, we have electricity and magnetism, and these equations seem to represent that they both are in contact, intermediately at least. So while we did notice some faults where rho dot plus divergence of u is equal to zero was violated, Maxwell further worked on that, and then he got it to this where where you can see that both the equations are maintain the law of contiguity. So the modified system of field equations permits the prediction of waves with finite velocity. In isotropic substance free of charges and currents, rho is equal to zero, u is equal to zero, d is equal to epsilon e, and b is equal to mu h. We finally get curl h is equal to epsilon by c, e dot is equal to zero, and curl of e is equal to mu by c into h dot is equal to zero. This seems fairly simple, where we just expand on these equations, but expand on the equations we saw in the beginning, but we equate current density and the overall density to zero, so that it's an isotropic substance free of charges and currents, so that we can finally obtain, and obviously the value is supposed to be zero. So taking the curl of one of the previous equations and using that formula for a vector with vanishing divergence, one has curl of curl, which is equal to minus delta. One obtains the wave equation for each component of E and H. So delta phi is delta phi minus 1 by C1 square, and the partial derivative of phi, and dt square is equal to 0, and C1 is equal to C by EU, epsilon, root of epsilon u. We can see how this gives us the value for velocity of propagation, which is basically C1, with relation to the speed of light, the electromagnetic constant C. So in this context, the constant has dimensions of velocity and can be measured by determining the magnetic field of a current produced by a condenser discharge, and is therefore measured electrostatically. Such experiments had been performed by Kohlrausch and Weber, and the result for C agreed with the velocity of light in vacuum. So this result basically agreed with the velocity of light in vacuum. Whatever we got, the value for C, that was maintained. So therefore, we finally see some connection right there. This evidence for electromagnetic theory of light was strongly enhanced by experiments carried out by Boltzmann, which showed that the velocity of light in simple substances, rare gases which are monatomic, can be calculated from the dielectric constant epsilon, with u being equal to 1, with the help of formula for C1 in this equation. The equations got mislabeled. It's actually equation 20. So the Maxwell's formulation satisfies contiguity, as you've seen, but its relation to Cauchy's form of dynamical laws has still to be established. We will not look at Cauchy's laws, because they go a little off topic, and they don't really seem to explain much about contiguity, and what I found right here seem to explain about contiguity. But I will talk a little more about Maxwell's equation and its connections to Lorentz force. So electric and magnetic field vectors, though they are originally defined by the forces on point charges and magnetic poles, which actually do not exist, are defined by the equations also in places where neither charges nor currents exist. The law of this connection has also been found by Maxwell. It is a mathematical formulation of Faraday's intuitive interpretation of mechanical reactions between electrified and magnetized bodies. Apart from the electric force in the charge, F is equal to epsilon E, there also exists a mechanical force on the element of linear current U produced by a magnetic field H. So this force is perpendicular to H and the current U, and therefore it does not work. It's not quite uniquely determined, as one can observe and obviously add any force whose line integral over the closed circuit vanishes. the simplest expression is F is equal to 1 by C U over B, as can be seen by considering the change of magnetic energy 1 by 8 pi into H into B dV produced by a virtual displacement of the element of current. So to illustrate Maxwell's procedure, it suffices to consider charge distributions in vacuum with density rho and current U. Basically, the current density U is equal to rho by rho V. Sorry. Combining the two forces, F is equal to epsilon. Sorry, small correction right here. Epsilon E and F is equal to 1 by C U over B into one expression. We have an expression for the density of force, where force density is equal to rho into E plus 1 by C into V over H. So this seems to mirror Lorentz force. Therefore, we can see how Maxwell's equation maintains continuity, and even to this day, it's used relevant to Cauchy's momentum equations and even in general relativity. But we will look at, but just to show the concept of continuity, I have limited myself to explaining about just the four equations and expanding upon them a little. So that's all for Maxwell's equations. Next, we'll be looking at relativity. So Arthur Eddington, who performed the Eddington experiment, which confirmed Einstein's theories, he did while that did help with furthering Einstein's theory in 1915. He said that results could have been obtained, or even could have been obtained by pure reason using epistemological principles. This seems like a rationalist view, like we've seen before in the whole rationalist versus empiricist debate. So that's not what we need in relativity, since it seems a little more while Einstein was a realist, there were some instrumental foundations to this. There was a philosophical urge behind Einstein's effort. In particular, the violation of continuity in Newton's theory was unacceptable to him. So the greatness of his achievement was just that he based his own theory on hard facts which are obvious, but they were overlooked or unnoticed in Newton's time as well. Now, you might ask me, in the previous talks, you did say that Newton did stick to the law of continuity, right? Well, the truth being that he only stuck to them partly. He considered Earth and the Sun. He considered Earth and the Moon and the actions between them. Of course, they're intermediate, but one thing is that he never considered that these two were in contact with each other. Like there was of course a force, but as Newton's general relativity proved that there was the idea that gravity is merely an illusion. So you really can't give it that much credence, and therefore there was a slight violation of continuity. But in Einstein's time, it was made much more obvious because there were some obviously overlooked facts. So we could often look at the main fact that the identity of inertial and gravitational mass, which Einstein expressed as the principle of equivalence between acceleration and gravitation. And we can consider this example. An observer in a closed box cannot decide by an experiment whether an observational acceleration of a body in a box is due to the gravity produced by external bodies or to an acceleration of a box in the opposite direction. So this is a good example of what I just explained before this. Basically, the idea that Newton didn't consider that these weren't in close contact with each other. So this principle means that arbitrary non-linear transformations of time must be taken in consideration. Newton's theory was fairly linear in its ideas, and it's quite easy to be understood by even people who went to high school. But when we get the idea of Minkowski space-time and all the non-linear lines, all the non-linear idea of space-time, it makes it very improbable that transformational spaces should be linear. So this was corroborated by considering rotating bodies. A volume element on the periphery should undergo a peripheral contraction according to the results of special relativity, but remain unchanged in the radial direction. Hence, acceleration was necessarily connected with deformation. So as it accelerates, there is deformation taking place. So this led to the postulate that all laws of nature ought to be unchanged, or rather covariant, with respect to arbitrary space-time transformations. But as special relativity must be preserved in small domains, in postulate of invariance, the line element had to be made. So we had to consider the introduction of the line element is being explained right here. So, given the whole non-linearity of space-time and the introduction of Minkowski space-time, which included three-dimensional space with one dimension of time, so that led to us concluding that there's a line element. So, long struggle of Einstein to find a general covariant field equation was due to the difficulty for a physicist to put together mathematical ideas necessary. It seems a little ironic since Einstein was quite good at mathematics, but let's not just go by this because his work was more relevant to physics. So the ideas which were made, which completely worked out by Riemann and his successors. So the physical significance of the line element seems rather mystical in general, genuinely continuous spacetime. If it is replaced by the idea of affine connection, where you have two spaces connected by a non-linear line, the impression of the mystery is further enhanced. But the appearance of a finite length in ultimate equation of physics could be expected. The quantum theory is the first step in its direction and introduces not a universal length but rather constant. And this constant is none other than Planck's h bar, the pure value of Planck's constant of the dimensional length times momentum into the laws of physics. So there are numerous indications that the further development of physics will lead to a separate appearance of these two factors. H bar is equal to Q into P in the ultimate laws. So the difficulties of present day physics, or rather, I would say modern physics, since a lot of work is being done in this field and every day new developments are coming. So they're centered about the problem of introducing Q in a way it satisfies the principle of relativity. This finite length should be introduced. So this seems to indicate that relativity needs a generalization where infinitesimal element Ts is replaced by a finite length. So this whole part about the finite length was a little bit of the comment from Max Born in his book Natural Philosophy of Cause and Chance, which we primarily refer to for these talks. So that concludes this. That concludes our talk series for philosophy and physics, where now we looked at some examples in physics. Of course, there's a lot more in physics and a lot more places where philosophy used unknowingly or knowingly. But this talk series was more of enabling you and anyone who watches this to have a little bit of consideration towards these ideas so that they'll approach physics from not only the idea that, okay, it is merely a science, but rather treat it as, something that explains the world around us, or if you're an instrumentalist, something that like the usefulness of the tool, so on and so forth. So, regardless of whatever you choose to see, there is the idea of causality, cause and effect, which is very, very important in physics. And contiguity and antecedents are like two very prime concepts that are applied in this. Today, with Ashwin's talks, we looked with how Kepler and Newton worked on these laws, and with the sections of Maxwell and relativity, Maxwell's equations and relativity, we looked at contiguity and how they were followed in these equations. And also these ideas in terms of relativity, because we didn't look at much equations relativity. So that concludes the talk for today. Thank you.